This is problem 9 from the review problems. And what we have is we have a mass, M1. So this is M1 on a frictionless table connected by a string through a hole in the table and is attached to mass 2. And M1 is rotating in a circle of radius r and the hanging mass remains at rest. So this is not moving in the z direction. So the first thing we have to do is draw a free body diagram for both masses. The second thing we need to do is we need to analyze the forces on the hanging mass to determine the tension in the string. And then finally, we need to find the speed of M1 to keep M2 so that it remains hanging at rest. Okay, so we've got our givens. And we don't have any numbers in this problem, so we're going to be representing everything with our variables. So we're given M1, M2, the radius is capital R, and so we're looking to find two things. One is tension, and the other one is the velocity. So we have this picture that looks like this, where, right, and so we've got our mass 1 right here. This is radius R to the center. And then we have a string with like a mass M2 hanging down. This is M1. And so the first thing we need to do is draw a free body diagram for each. So we're going to do M1 first. And M1, the free body diagram is the normal force by the table. And that's equal to the force of gravity down. So these should be about the same length arrows because M1 is not moving in the z direction, so they should be equal. And then it also has, this is a string, and so there's a tension towards the center. So this is my tension. For M2, I only have the force of gravity, and it's balanced by tension, so these should be equal and opposite because it remains in the z direction. It's not moving up or down. All right, so B, analyze the forces on the hanging mass to determine the tension in the string. So what we're going to do is the sum of the forces. We're going to look just in the r direction. So we have, right now we have r theta. We're talking about polar coordinates. We're just thinking about r and z. And we don't have to worry about z because we're talking about tension. And so we're going to use the tension to do the calculation. So let's talk about the M1 first. So we've got force in the r direction is equal to ma, and because it's moving with in circular motion, it's going to be mv squared over r. And so in the r direction, the only force acting on M1 is my tension. So I have tension is equal to mv squared over r. And now, well, thinking about M2, the only forces we have are the forces in the z direction, and that's equal to ma, and because we're not moving, that's equal to 0. So my forces in the z direction are tension is up, minus Fg is equal to 0. Tension is equal to Fg, and that's equal to M2G. And this over here, this is equal to M1. So if I want to, so I'm looking to determine the tension in the string, and so if I want to solve here for tension, I just know that tension is equal to M2G, right? So I've got my tension is equal to M2G, so that's the first thing I needed to find. And so that's part B, so this is B. And then for C, I'm looking for the speed. So I can use what I found, all I needed to do for B was this part of the equation of the problem. This allowed me to solve for the tension, and now I can use this really, I can call this part C. And what I'm going to do is I'm looking for V here, so I'm going to rewrite the equation. I'm going to multiply both sides by R, right? And I'm going to have M1 V squared is equal to R. And here I changed my R a little bit, right? This was R, this is R. Let's make them the same because they're the radius. So let's be consistent. So this is R. This is going to be my R times T. And now to find V, I'm going to divide by M1 on both sides. So that's going to be R times T divided by M1, and then this was squared, so I'm going to take the square root. And that's it. That's your answer.